Thank you very much for the introduction. I want to thank the organizers for inviting me. It is a great pleasure to be for the first time here in this institute. I've heard a lot about this. I have many colleagues who passed here, and I'm very excited to be here. And also let me say that this is my second visit in Korea, and both of my visits are related to the IMU. And the first time I was here was for the ICM in 2018, where I was a member of the 2014, sorry. I was a member of the Brazilian delegation, and we were here mostly with the purpose of learning how to organize an ICM, because 4 years later we organized it in Brazil. And I can now confess that at that time you scared the hell out of us, because everything was organized so neatly, perfectly, that we were wondering whether we would be able to, match this kind of organization in Brazil. So we paid attention to every single detail, and everything was really spotless. We copied you as much as we could, and so thank you very much for inspiring our work at that time. I decided to present a talk which has the goal of introducing you to my current research, which is related to conformal geometry. But most of the talk will, in fact, be a motivation for my recent research. So I would hope that this is accessible to a wide range of researchers. So conformal geometry is a geometry where you have a manifold and you assign on each tangent space the notion of an angle between two tangent vectors, not of a length, just an angle, okay? And usually this is, the model for this is you take a Riemannian manifold where you have an inner product defined in each tangent space, but then you are allowed to change at each point. You are allowed to rescale the inner product as you wish. So you can multiply that metric by a function, by a smooth function, and then you have a conformal structure that depends on the choice of a Riemannian metric and a choice of a function. And that's where geometry meets analysis, because you have a Riemannian manifold, but then you have a function in front of it, which is where you apply differential operators. So conformal geometry is a natural ambient for both PDE theory and Riemannian geometry, okay? And in particular, my work is related to the notion of curvature. It's not clear what one has to define, how one has to define curvature in conformal geometry. And so let me start with describing what curvature is in all the theories that we've known since we're freshmen at the university with our first geometry courses. Let me see if I get this straight. Okay, let's see, yeah. So curvature is a unifying concept in geometry, which is related to metric. So let's assume this definition. So curvature in some geometric theory is a quantity that measures the local deviation of a given structure from the linear model of that theory. So we're assuming that if you have a geometric theory, there's some linear model in that theory, and that has to have curvature 0. So whatever measures distant from this linear model, we call curvature, okay? So for instance, if you take curves, the curvature tells you how much the curve is not a straight line. The straight lines are the linear model for one-dimensional geometry, right? If you take a surface, then for surface theory, the linear model are planes. So the curvature of surface is a function that measures how non-planar is the surface, okay? And in Riemannian geometry, the linear models are Euclidean spaces, which have curvature 0. So a curvature is something that measures how much a manifold is non-flat, non-Euclidean. And so by the end of this talk, we should be able to say what is the right notion of curvature in conformal geometry. But there's a caveat, very important caveat, which is there are geometric theories that have no curvature according to this definition. And the most notable example is the case of symplectic geometry, because there's a famous theorem in symplectic geometry, it's called the Darboux theorem, that says that you can't distinguish locally any symplectic geometry from the linear model. So every symplectic manifold, given any point, there's a neighborhood which is symplectomorphic to a neighborhood of R2n with a canonical symplectic structure. So let's say that there's no curvature in symplectic geometry, at least according to this definition. And let me say that, in fact, when I first moved to Brazil, one of the first talks that I've seen by Manfredo do Carmo, he defines geometry, in fact, as a study of objects that have curvature. So when he gave a talk and talked about what the geometry in Brazil, he started by saying, so I'm talking about geometry, which excludes symplectic geometry, because that doesn't have curvature. Okay. So the two questions that I want to address with you is a question of rigidity. Suppose that you know the curvature of a space. Can you characterize the space? So can you know what the global geometry of a space is by looking at just by knowing the curvatures? And this is usually depends on the existence of some structural equations that describe the geometry using curvature. And then the second problem is, suppose now that you have a given structure, and can I deform that structure in a given class set that the curvature becomes easier, say constant, for instance, 0 or constant? So these are the two questions that I would like to answer with you. And in that case, how many deformations can one have to make the curvature of a space constant? Okay. So let us look at really easy examples. Let's look at curves in the plane, okay? So there are no invariant of a one-dimensional curve except for arc length, okay? So this is the unique invariant of a curve. There's no intrinsic notion of curvature. But there is an extrinsic notion of curvature, that is, so suppose you parameterize your curve by arc length, then the gamma prime will give you the unit tangent vector at each point, and the curvature is the rate of exchange of this tangent vector, so it's the second derivative, the absolute value of the second derivative. This is what students define as curvature of a curve, right? Clearly this is 0 exactly when gamma is a straight line. As far as the rigidity problem, the curvature tells you everything about the curve. So if you have the curvature function, you can recover up to rigid motion exactly what the curve is like. When you go to the space, then there is another curvature-like invariant, which is called the torsion, of course, which measures the deviation from planarity. That tells you how much the curve is non-planar. And that is defined using, remember this, the Frenet-Serret frame, the tangent, the normal, and the binormal, right? The torsion is the inner product between the derivative of the binormal with the normal. So this is 0 exactly when the binormal and the normal are in a sense, when they're fixed, they are constant, so that means that the curve is planar, okay? So there are two curvatures here, torsion and the regular curvature, and the fundamental theorem of curves tells you that if you have curvature and torsion, again, you can recover the curve up to rigid motions. And this is done using these structure formulas given by this, you probably remember from your differential geometry book, that basically when you have torsion and curvature, you can solve the system, find the tangent vector, and then you integrate and you find the curve. So again, in the case of curves in spaces, the curvature gives you rigidity. There's also a higher dimensional extension of this fact using, if you take curves in higher dimensional spaces, you have this generalized curvature, and you have a totally analogous theory. When you go to surface in space, what is this? Now something interesting happens. So you take a point of the surface and you define a curvature to be something like the average of all of the curvatures of all curves on the surface passing through that point, okay? So you can take, rather than taking any curve through P, you can take only curves that are obtained by planar sections. And then if you're smart enough, you understand that in fact, rather than taking any planar section, you can take normal planar sections, okay? So to each normal plane, there is associated a curvature, right? So you define principal curvature to be the minimum and the maximum of these normal planar curvatures. This is more or less the picture. And then you have to take an average of these two numbers, and there's two types of average that we want to, that one can consider, either the arithmetic mean, that is called the mean curvature. Oops, I don't think the pointer works. And then you can take the product of them, okay? And that is the Gaussian curvature, so two notions of curvature here. Mean curvature and Gaussian curvature. And the main result by Gauss, of course, is that this K is in fact intrinsic. This depends only on the metric induced on the surface by the ambient, and not by the way the surface is embedded inside the ambient, okay? So this is the famous Theorema Egregium, which was proved by Gauss in early 19th century. He proved this by showing that in fact K measures an area defect. Like if you take a small piece of surface, you look at the area and you compare it with the area on the tangent plane. K is the ratio between these two numbers. And also, the theorem of Gauss-Bonnet tells you that if you integrate the curvature on the surface and assume that S has no boundary, for instance, then you get a topological invariant, which is given by the Euler characteristic of the surface. So that in fact, knowing the curvature also tells you about the topology of the surface. Okay. So what about deformation of curvature for surfaces? The most important theorem is called the uniformization theorem that tells you that, okay, this was formulated maybe by Poincaré and proved maybe the end of 19th century, beginning of 20th century, something like that, proved by, say, Poincaré, Klein, and Koebe. It says that if you have a simply, well, okay, this is a modern statement to the theorem. If you have a surface which is simply connected and complete, then you can change the metric conformally to make it become either a sphere, a round sphere, or a Euclidean plane, or a hyperbolic space, hyperbolic plane, okay? So there's basically like two-dimensional conformal geometry basically reduces to the study of these three spaces, okay? This is a very important theorem. It has very deep consequences. And so it gives canonical models for Riemannian surfaces, and also, okay, and this is also lays the foundations for the study of geometric PDEs in the study of conformal metrics. Okay, so let's now look at the curvature on surfaces introducing differential operators. So on a surface, there is a differential operator, which is the Laplacian. which in local coordinates has this formula here. So the Gij with the lower index are the coefficient of the matrix, and the Gaj upper index is the inverse matrix. So suppose that you have a surface M2, then the Laplacian of a function defined on M2 is defined as this operator here. So it's a second order elliptic operator. Ellipticity comes from the fact that the matrix Gij is positive definite. And in fact, it's not hard to show that this operator doesn't depend, like this is a coordinate expression of it, but in fact, this operator is defined independent of coordinates. So it is an invariant of the surface. And for instance, if the metric is conformally flat, so if the metric is just like a flat metric dx squared plus dy squared times a function e to the 2 omega, then the Laplacian is simply the inverse of this conformal factor e to the minus 2 omega times the usual Laplacian, okay? And, okay, so this is the important point, that if you make a conformal change of the metric, that is, if you take a metric which has the form, you multiply g by this factor e to the 2 omega, the Laplacian also transforms in a similar way, with the inverse of this factor, okay? So, like here there's a formula missing. So, maybe I should write here the formula. If you compare the curvature of a metric G and of a conformal metric G tilde, these two are related by an equation which is called the, Liouville's equation. It's missing from there. It is something like, so you apply the Laplacian to omega plus the curvature of the metric G times e to the 2 omega is equal to the curvature of the metric G tilde. This is the formula that's missing from here. This is called Liouville's formula. Okay, so that tells you that the Laplacian is related to the curvature when you apply a conformal change. So that is one of the main points that I want to make. Conformal changes of the metric transform the curvature in a way which involves elliptic operators. So that's one of the points that I want to make in this talk. Okay, when we go to Riemannian manifolds, then we consider a manifold of dimension n. This generalizes the theory of surfaces, and it was introduced by Riemann, of course. So we have at each point x of the manifold, we have a positive definite matrix Gij, which in coordinates gives you the metric. And then when you have a Riemannian manifold, you can do all sort of things you like to do in geometry. So you have, you can measure length, angle, distances, geodesics, volume, area of surfaces. You have a connection called the Levi-Civita connection. You have parallel transport. You can consider these differential operators gradient and divergence. And you have Laplacian, which is a combination of divergence and gradient, of course. And then the curvature tensor is defined as the lack of commutativity for the Levi-Civita connection. So if you take coordinate fields del I and del j, and you apply this iterated covariant derivative to vector field z, then the curvature tensor is defined to be this difference. And this is in fact a tensor, it's easy to show, and which is 0 exactly in the case of flat metrics, okay? So this is the coordinate definition of the tensor, but if you want a coordinate free, then you have to introduce this term with the Lie bracket. So this is a 1,3 tensor, which which is the right notion of curvature for Riemannian manifolds. Okay. So let's look at the question whether the curvature can be used to describe the Riemannian manifolds. Okay. There is a very important theory which was introduced in the first part of the 20th century, in 1920s more or less. It's called the Weil's invariant theory, that tells you that so you want to study what are all the local geometric invariants of a Riemannian manifold, okay? And the theorem says that if you have a scalar invariant of a Riemannian metric, that is necessarily a polynomial function in the curvature tensor, the coefficients of the curvature tensor, or its covariant derivatives, or the metric tensor. So the metric, the curvature, and the covariant derivative of the curvatures will be the only scalar invariants associated to Riemannian manifolds. Okay. And also tensorial invariants can be defined using similar construction. So basically, the curvature tells you everything about a Riemannian manifold. Another way of studying the problem of whether curvature determines, at least locally, a manifold can be stated in terms of another famous theorem called Cartan-Ambrosen-Hicks theorem, that tells you the following thing. Suppose that you have two, okay, I'm giving here the real analytic version of this here. Oh, wait a second, do I have the, oh, sorry. I have to tell you what the thesis of the theorem is. Okay, so suppose you have two Riemannian manifolds. You choose a point here and a point here, P and Q, and you choose a linear isometry from TPM to TQN, and you want to know whether this map here is the differential of a local defined isometries between a neighborhood of P and a neighborhood of Q. And this is true. The positive is yes, exactly when all the covariant derivatives of the curvature tensor here are pulled back to the corresponding covariant derivatives of the curvature tensor here. So basically, if the curvature tensor and all its derivatives coincide at some point, then the metrics coincide in the neighborhood of that point. I apologize, the statement of the theorem comes in this part here, which is not shown. I should have used a smaller font in this theorem here. Okay, so let me now describe a little bit about the problem of perturbation of a metric, of deformation of a metric in a class. So this is the higher dimensional version of the uniformization theorem for surfaces. Let me tell you about the Yamabe problem, which was formulated in the 50s by this Japanese mathematician called Yamabe, of course. And the problem is like this. So suppose you have a compact Riemannian manifold with dimension greater than or equal to 3, dimension 2 being the trivial case. So you want to know whether you can perturb the metric G to a conformal metric G hat for which the scalar curvature is constant. The scalar curvature is like an average of all curvature of surfaces inside the manifold passing through that point, okay? So it's a scalar invariant. So this is the Yamabe problem. Of course, in dimension 2, this is exactly the answer is yes by the uniformization theorem. But in dimension greater than 2, this is a much harder problem. And it involves a certain differential equation, which is called the Yamabe equation, which has this form here. So if you're smart enough to write the conformal metric as a, if you write the conformal factor rather than as a function, you use u to this power 4 over n minus 2 related to the dimension, then this will become a nice elliptic equation on u, provided that you used exactly that power over there. That was one of the discoveries of Yamabe. And so you get to this equation here, where an is a dimensional coefficient. So basically, Laplacian of u plus a constant times plus a function times u equals a parameter lambda times u to this power, n plus 2 over n minus 2, which is not equal to 1. So this is not a linear equation, and the nonlinearity is given by this number n plus 2 over n minus 2. Now it happens that this is a very special number. Analysts know this number very well, and it's called the critical Sobolev exponent. What this means is that the space, the Sobolev space H1 embeds into LP in a compact way, provided that P is less than this number, okay? What this means is that this equation here, okay, if you take a similar equation with a power of u, which is less than this number, a positive solution for this equation would always exist, okay? On the other hand, if you take an equation of this type, where the power of u is larger than this number, a positive solution never exists. So this is precisely the number for which it's not clear whether you have a solution, a positive solution for this equation or not. Okay, this is exactly the very interesting case in the theory of elliptic PDEs. The study of nonlinearity of nonlinear equations lead exactly to this kind of analysis, studying what happens for these critical exponents. Okay, and it happens that every time that you have a problem in conformal geometry, for which some equation has to be constant, the corresponding equation is always of this type. So criticality for PDEs is the same as conformal invariance. So there is this very nice analogy between a classical analytical problem with a geometric problem. So solutions for this equation are, in fact, extremal points for a functional, which has this definition that may look a little complicated, but what it turns out to be is the denominator here is just the integral over m of the scalar curvature, and the denominator is the volume of the conformal metric. Observe that the Yamabe problem is a homothety invariant problem. That is, if you have one solution g hat of the problem of the Yamabe problem, then you can multiply this g hat by any fixed positive number, and you have another solution. So you need some kind of normalization, and this is the normalization that you need in order to make the solution, say, unique. So the Hilbert-Einstein functional of a conformal metric is given by this ratio here, and it's up to a volume normalization. It's just the integral of the scalar curvature, okay? Notice that the coefficient that appears there only depends on the dimension. So the Yamabe problem has a positive solution whether you can, if you can prove that this functional here admits a minimum, say, in the space of all positive functions on M, okay? And so in order to solve this, it took about 25 years to find a complete answer to this problem. And the answer was obtained finally in the 80s with the following theorem. So you consider the infimum of this Hilbert-Einstein functional, and you call this the Yamabe constant of the manifold. Oh, okay. Yeah, there's a pointer here. And then the theorem says the following. So this is due to a combined effort of these four mathematicians, Yamabe first, and then Schrödinger, Aubin, and Schoen. It says the following. So suppose that you have a compact manifold of dimension greater than or equal to 3. Then in first place, this infimum is a real number. That is, it's greater than minus infinity. The second result, which is due to Aubin, is that among all possible compact manifolds of dimension n, the round sphere of dimension n is the manifold that maximizes this infimum, okay? So given any manifold M, you always have this inequality here. So that means that in particular, this quantity is also bounded from above. And not only that, but there's also rigidity. If you have equality in this inequality here, then this manifold M has to be conformally equivalent to the round sphere, okay? The third property is that, in fact, this infimum is a minimum. It is always attained, so this means that the Yamabe problem always has a solution. Besides, if this infimum is negative, the Yamabe problem has only one solution, okay? So for the deformation of scalar curvature, the answer to the existence of a deformation which makes the scalar curvature constant is positive, okay? All right. Now let's see how the scalar curvature is related to the Laplacian. For higher dimensional manifold, the correct analog of the Laplacian is the so-called conformal Laplacian, which has this form here. So it is the classical Laplacian plus a multiple times the scalar curvature, okay? Why this? Because this is what makes this is the operator that transforms correctly when you make a conformal transformation of matrix. So if you pass to a metric G hat, which is given by this conformal factor times G, then the conformal Laplacian transforms into this operator here, which is exactly the way the classical Laplacian transformed under conformal invariance in dimension 2. So if you want to go to a higher dimension, the Laplacian is replaced by the conformal Laplacian, which is just this, the Laplacian plus a zero-order term, which is a curvature, okay? So this now leads to the definition of what is a conformally covariant differential operator. Once we understand that curvature is related to differential operators, in particular to those that transform well under conformal transformations, then one can give this definition. You say that a differential operator on a Riemannian manifold is conformally covariant if it satisfies exactly the same property satisfied by the conformal Laplacian that I've just shown you. That is, when you do a conformal transformation, then basically the operator gets multiplied by the same conformal factor, by the inverse of that factor, okay? Examples of these conformally covariant operators include another famous operator in conformal geometry, which is called the Panitz operator. The Panitz operator is a fourth-order operator, which has a very weird definition, which you can see here. Oh, sometimes the pointer works, sometimes it doesn't. Or maybe I'm pointing it in the wrong way. But basically what's important to notice is that the principal part is the square of a Laplacian. The rest is a whole bunch of things, curvatures of various type, scalar curvature, Ricci curvature, scalar curvature again, and then there is this new term, QG, And all the coefficients that appear in this equation are dimensional constants. They only depend on the dimension, okay? So there is a new curvature popping out here, which is this Q curvature. That's the zero order term of this differential operator. So we see that all the coefficients are curvatures here, okay? So this leads, okay, so, and this operator satisfies the conformally covariant equation, and I'll tell you why later, because you can't really check this if you use that I mean, it's a very involved calculation to show that for that operator this equality holds. There's a smarter way of doing that. Okay, so ready to propose the notion of conformal curvature. I say that a conformal curvature is a quantity that appears as a coefficient of a conformally covariant differential operator. So like, in this case, the Q curvature appears as the zero order term of this conformally covariant operator. Then I would define a conformal curvature, everything that is a coefficient of a conformally covariant operator. Okay? And one has to notice that conformally covariant operator in general exist, but their existence may require higher dimension, which in a sense is natural to expect. Every time you define a new notion of curvature, you have to increase dimension in a sense. It's like when you go from, curvature to torsion, or to even Ricci curvature doesn't exist in dimension 2, for instance. So you really have to increase dimension of the manifolds in order to define these conformal curvatures. Okay, how does one obtain conformally covariant differential operators? This seems to be a quite challenging task. But then there's two very nice theories. Well, maybe this is my connection with fields. I didn't think I had field medalists in my talk, but I do have Pfefferman here, so I am relieved. So there's two theories due to basically to the school of Pfefferman that tell you how you can obtain invariants for conformal manifolds. And okay, in order to tell you the general theory, let me tell you the very special case of the sphere. Okay, so you can think of the sphere Sn as a section of the light cone in Rn plus 2. So you take Rn plus 2, you put a Lorentz metric in Rn plus 2, you take the light cone, which has dimension n plus 1, and you take a section, a planar section, and you obtain a n-dimensional sphere, right? So what happens is that the metric invariants of the ambient space, of this Minkowski space, correspond to conformal invariants of the sphere here, okay? So Pfefferman, together with other researchers from the school, he generalized this to a general, a compact conformal manifold. And he showed that you can always embed a conformal manifold inside a higher dimensional space, which has a pseudo-Riemannian metric, which is Ricci flat, exactly like Minkowski space, and the manifold is embedded as a hypersurface inside the light cone of this Ricci flat Lorentzian or a pseudo-Riemannian manifold, okay? And the pseudo-Riemannian invariants of the ambient correspond to conformal invariants of your original conformal manifold, okay? So you pay the price of going to a higher dimension, but then you get that the metric invariants of this ambient space correspond to the conformal invariants of your manifold. Of course, in general, this is just a local construction around the manifold. So basically, you define the ambient space by finding the Taylor coefficient, the Taylor expansion of the metric near your conformal manifold, okay? So this is one of the two constructions. And the other construction is called the Poincaré metric construction. And here the example is, again, of the sphere, which is now seen as the conformal infinity of the hyperbolic disk, okay? So basically, your sphere, this is the boundary now of an n+1 manifold, which has a metric, like here you take the disk metric, the Euclidean metric of the disk. But if you divide this metric by the distance squared to the boundary, you get a metric which satisfies as, well, it's a solution of this equation. So Ricci is now, it's non-flat, but it's, so this is like an Einstein equation. The Ricci of the metric G hat is a negative multiple of G hat itself. So your metric in the ambient manifold is hyperbolic, and this is the conformal infinity. And again, the metric invariant of this hyperbolic manifold correspond to conformal invariants of the infinity, okay? So in this case, compared to the ambient metric construction, here you have a lower dimensional space. You only need to add one dimension, but you have a slightly more complicated metric. It's not Ricci flat. Now it has this asymptotic hyperbolic metric that satisfies this Einstein equation. So these two are very important construction, and they allow to define a whole lot of conformal invariance objects, including the Q curvature that we have already met, and a lot of other notion of curvatures, renormalized volume coefficients, the so-called sigma K curvatures, and also a whole family of conformally covariant differential operators that are called GJMS operators. Let me see what time it is, and I'll tell you. And I'll see how deep I can go. Okay. So maybe I should go a little faster here. So let me tell you briefly about these GJMS operators. These were operators discovered in 1992 by these four mathematicians, Graham, Jen, Mason, and Sparling. And they have the property, okay, so this is a family depending on parameter k, where k is greater than or equal to 2. And, greater than or equal to 1. When k is equal to 1, this is simply the conformal Laplacian. When k is equal to 2, this should be, let me say it again. K is an even number, and when k is equal to 2, the corresponding operator is the conformal Laplacian. When k is equal to 4, it's the Panitz operator, but there's a whole family of them. And what they do is that they're conformally covariant differential operators, but their higher order term is simple. It's just where is it written here? Let's find the conformal metric. Yeah, I'm sorry. There's something missing, which is the PJK has the highest order term is a power of the Laplacian, is a k over 2 power of the Laplacian. So here we have the Laplacian when k is equal to 2. For the Panetz operator, this is a square Laplacian. For k equal to 6, this is the cube power of the Laplacian, and so on. So these constructions give you a whole family of conformally covariant operators, and the corresponding coefficients are conformal curvatures, okay? So let me maybe finish with something to show you a little bit about a result of my research. So let me show you how one can obtain multiple results for existence of Yamabe matrix, so a special case, k equal 2, in a case of a non-compact manifold, okay? So the classical Yamabe problem has to do with compact manifolds, and now I want to take a look at a case of non-compact manifold. So I want to consider the singular Yamabe problem on a space which is obtained by removing a k-dimensional sphere from an m-dimensional round sphere Sm. So I remove, say, an equator from Sm. And the problem that I want to study is to find the metric on this non-compact manifold, which has to be complete. It has to be conformal to the round metric and has to have constant scalar curvature, okay? So clearly the round metric has constant scalar curvature, but it's non-complete. So the problem is whether I can find a complete one. For non-compact manifolds, the correct formulation of the Yamabe problem is to require that the metric has to be complete. This is like a condition at infinity for the metric. So this is the problem I want to study. And the theorem is that if k is not too big, well, if k is greater than n over 2, then half of the dimension of the space, there is only one solution that I will describe in a second. But if k is less than half of the dimension, in fact, there's infinitely many solutions for this problem, okay? This is a particular case of a similar result that holds for in a much larger generality. Let me show you the proof of this to finish my talk, and the proof should follow this picture here, which let me see if I manage to convince you that this makes sense. So this involves several arguments. So I start from Sn minus Sk and observe that this is the same as Rn minus Rk from a conformal point of view using stereographic projection. And if you write in a smart way the Euclidean metric in this space, you will find that after dividing by r squared, you get the product between a hyperbolic space and a sphere. So Sn minus Sk is conformally equivalent to this metric, to this manifold here with the product metric. So hyperbolic space times a sphere. This is constant sectional curvature. This is constant sectional curvature. So the product has constant scalar curvature. So we have one solution for the singular Yamabe problem simply by taking stereographic projection, division by r squared, and that's what you get. So that's one solution. When k is greater than n over 2, the value, you see, when k is large, this is negative curvature, this is positive curvature. So when k is large, this object will have negative curvature. And in case of negative curvature, there's only one solution for the Yamabe problem. So when k is greater than n over 2, this is the only solution that we get. Clearly this is complete, right? This is complete times a compact. Okay, so what do we do when k is less than n over 2 to get the other solutions? Well, first we observe that the hyperbolic space is non-compact, but it has lots of compact quotients. And these are hyperbolic manifolds, okay? So we can take, rather than this space, a compact quotient given by a compact hyperbolic manifold times a sphere, okay? So sigma times a sphere. Now, the fundamental group of a hyperbolic manifold is residually finite. What that means is that it admits an infinite tunnel of finite index normal subgroups. Okay, this is what residually finite means. This comes from a famous theorem called the Selberg-March lemma that says that if you have a finitely generated algebraic group, it has to be residually finite. So that means that this hyperbolic manifold has an infinite tower of finite coverings, like this, more or less. Okay? And so we have this infinite tunnel of coverings like that. So what we do is we take the solution of the Yamabe problem in this space here. This is a compact manifold. So the Yamabe functional has a minimum here, and we take it here, and we pull it back here. And then we pull it back here, and then we pull it back. And then we look at the energy of this solution, the Yamabe, the Einstein-Hilbert functional applied to these pullbacks. And the thing is that the volume here increases while the scalar curvature remains the same. So when you compute these pullbacks, the energy goes to infinity, So if the energy goes to infinity, at some point, this energy must pass the value of the Yamabe functional on the round sphere. Remember, the round sphere had the highest possible value of the minimum of the Yamabe functional. So these solutions that you obtain by pullback at some point can no longer minimize the Yamabe functional. So there must be another solution given by the minimum, because the pullbacks at some point cannot be the minimum. So we start with the minimum here. When we pull it back, we get something which is not a minimum here. So we have another solution here, which is given by the minimum. And then we can start putting back this new minimum until it becomes, again, with infinite energy again. I'm sorry, with high energy again. And we get a third solution by taking a minimum. And this construction can be repeated, can be repeated infinitely many times here backwards because of this property of the fundamental group being residually finite. And so this gives infinitely many solutions on the universal cover, which is given by this manifold here. Why did we use this condition here? Well, because when we pull back and we want to make sure that the scalar curvature is positive, so that when we pull it back, it goes to infinity and not to minus infinity. And so this is where we use this condition that the dimension is less than n over 2. I have the impression that my time is over. Right, very close. So maybe I can just skip the rest and show you just the picture of my collaborators for this, which are these ones here. These are my collaborators for this project on conformal curvatures. And thank you very much for your attention.